Just
and he will tell us about the structure of finitely generated subgroups of branch groups.
Okay, thank you very much for the invitation and the opportunity to give a talk. So can you see my screen?
Yes, it's okay.
Okay, perfect. So the title of my talk is about branch groups and finitely generated subgroups. So maybe first start with some motivations. Why do we want to study branch groups and why to study finitely generated subgroups? So branch groups, they were first defined by Grigorchuk in 1997. So there are groups with a rich subnormal subgroup structure. Subnormal subgroup is just like either a normal subgroup or a subgroup which is normal inside the normal subgroups and so on. So this class of groups contains example of groups with kind of exotic properties. So for example, you can find finitely generated infinite torsion groups of intermediate growth as the first Grigorchuk groups, amenable but non-elementary amenable groups. So this fact follow from the group being of intermediate growth, for example, and many other exotic properties. Also, branch groups naturally appears in the classification of just infinite groups, where a group is just infinite if it is infinite, but every proper quotient is finite. These groups, and I will give you the formal definition in a few minutes, but these groups are defined by a nice action on a rooted tree. So we have a nice geometric characterization of them that we can use for computation, for example. It's not all, but many of these groups are recursively presented. So they are not finitely generated, they are not finitely presented in general, they are finitely generated. But they still have a recursive presentation, meaning that we can still try to do algorithm computation on them. So, okay, now the second part of the title was about finitely generated subgroups. So first, branch groups, they are groups with a rich subgroup structure. So it's natural to look at the lattice of subgroups and try to study it. But finitely generated subgroups are quite interesting with respect to the profinite topology. So the topology generated by finite index normal subgroups and the left cosets. So a subgroup is radially finite if only if the subgroup 1 is closed in the profinite topology, which is for finitely generated group equivalent to the fact that C acts faithfully on a locally finite rooted tree. And for example, some application of this, if a group is radially finite, recursively presented, and as an algorithm listing all finite index normal subgroups, then the word problem is solvable. So example of groups satisfying all of these hypotheses are residually finite, finitely presented groups, but also many branch groups will satisfy these properties. Okay, and some branch group, which I will define in a minute, have the so-called congruent subgroup property, which implies that you have an algorithm listing all finite index normal subgroups. So basically, the congruent subgroup property means like the profinite topology on these groups agree with the topology coming from the automorphism of the tree, of T. Okay, so we define what is radially finite, but you can go further using profinite topology. So a group is said to be LOF, for locally extensively radially finite, if every finitely generated subgroup is closed in the profinite topology. So this is, of course, stronger than just being radially finite. Using this property, you can show that if the group is LOF, recursively presented, and as an algorithm listing finite index normal subgroups, then the generalized word problem is solvable, meaning like if I give you an element and I give you a finitely generated subgroup, you can decide whether the element is inside the subgroup or not. And okay, so there are many examples of such groups. And another property that might be interesting is so-called Ribbs-Zaleski property. So you take finitely many finitely generated subgroups, H1 to Hn, and you look at the product of this subgroup. So this product is not necessarily a subgroup, but it is a subset, and you can ask, is this product closed in the prefinite topology or not? So if this is true, like for zero subgroup, it just means like the trivial subgroup is closed. So it's equivalent to be residually finite. If the product just over one subgroup is closed, then it just is a love property. And Rilke-Zaleski saw is a strengthening of the love property. Few examples of groups satisfy this property. So basically finite groups, finitely generated abelian groups, and finitely generated free groups, as well as limit groups and some other examples, have this property. And we hope to show that some branch groups also possess this property. So now, okay, so you can also use the description of finitely generated subgroups to say something about weakly maximal subgroups, which are subgroups which are maximal among infinite index subgroups. And okay, this I would just skip. So branch groups are by definition groups acting on rooted trees. So as you just listen, okay, so here is knows the picture of a rooted tree. So here is a binary rooted tree. You have a root, and then every vertex has exactly two children. And these vertices, they are in bijection with finite words over the alphabet. So 0, 1 in this case. Okay. And when you have a rooted tree, you can define levels. So the first level is every vertex has distance 1 from the root. The second level, every vertex has distance 2, and so on. Okay, and here is a picture, which was described in the last talk. So the TV is a subtree of T rooted at V. So every vertices that lie below V. And you can define sections. So here, so I use another notation, just pi V of G is the restriction of G at V. So it's a section of an element below V. And it belongs to the automorphism of TV, which is isomorphic to automorphism of T. So whenever you have an element that fixes every vertices of level n, you can describe it as a product of its section. So for example, here, I have an element that fixes all vertices of level 2, and it's described as just G0, what it does under the leftmost vertex of level 2, and times G1, G2, G3. And a subgroup of automorphism of T is said to be self-similar if for every vertex V, the section of the stabilizer of V is still inside G. And self-replicating if, or fractal, if it's exactly equal to G. So if you study subgroup of the automorphism of the tree, then some subgroups will play some important roles. So stabilizer of vertices, point one stabilizer of levels. So you fix point ones every vertex of the level M. And also very important subgroups are rigid stabilizers. So the rigid stabilizer of some vertex V is element of G that fixes every element, every vertex that is not below V. So here in this example, you see like you might act below V, but outside of TV, you act trivially. And the last subgroup is the rigid stabilizer of a level, which is just the product of the rigid stabilizer of the vertices belonging to this level. Okay, so yes, this is, I just say something I defined before, subgroup congruence properties. It's not going to be very important later. So the main definition for us, so subgroup G of out T is going to be called branch if for every level M, G acts transitively on vertices of level M. And also that these subgroups, the rigid stabilizer, are a finite index inside G. A stronger notion is the notion of being regularly branched. So for this, to define it, you need the subgroup to be self-similar, and then you say it's regularly branched if you still want it to act transitively on the level M, but also like there exists some finite index subgroup K that in some sort contain copies of itself. So here, like for example, you see, so the subgroup K at V is every element that acts as element of K below V, and you want this to still be a subgroup of K. Okay, so yeah, as I said, this is a strengthening of the notion of being branched. Some example of this group, so the first we go to group, as well as Gupta-Sidki P groups, or torsion GGS groups, acting on some T regular tree for P prime. So all of these examples are regularly branched. They have the congruent subgroup property, they are recursively presented, and they have a bunch of other property like being infinite, just infinite, torsion, all of the maximal subgroups are finite index, and so on and so on. Moreover, so the first Grigorchi group was the first example of a group with intermediate growth, so some very exotic property. And so here, just like small examples to understand how it works. First Grigorchi group is a 3-generated group, but usually we describe it using 4 generators. So it acts on the 2 regular rooted tree. And here is the action of the generator. So A just switches the 2 vertices of the first level and then to nothing below it. And then P is defined recursively as fixing the first level and under the left vertex just doing A and C under the right one. And you have similar definition for C and D. So it means like, okay, so we know that P does A and C, but we also know that C does A and D. So P does A under the leftmost vertex, and then it fixes the vertex on the right, and below it, it does A and D, and then you can like copy and paste these pictures and have a full description of how B, C, and D act on the rooted tree. You can define similarly Gupta-Sidki groups, which act this time on the P regular rooted tree. So they are defined by using 2 generators. The first one is cyclically a permute element of the first level, and then B is defined as A on the leftmost vertex, A minus 1 under the next ones, and acting trivially, and then B again on the rightmost vertex. And you can generalize this to a more general setting, but okay, maybe I can skip this part. Okay, so if I give you some group G, subgroup of the automorphism of my rooted tree, if G is finitely generated regularly branched over some finite index subgroup K, then the following are finitely generated subgroups of G. Okay, because it's a finite index. Also, this copy of K acting on other vertices because they are abstractly isomorphic to K. But you can use these subgroups to find many other finitely generated subgroups of G. So if I give you a bunch of vertices incomparable, so meaning like V1 is not below V2 and V2 is not below V1 and so on, and I also give you a bunch of automorphism of K, then you can define what is called the diagonal subgroup. So it means like here, you choose 3 vertices, for example, the ones that are in black. And the diagonal subgroup defined by phi1 of K times phi2 of K times phi3 of K is all elements that act as phi1 of K below the left vertex, phi2 of K below the second one, and phi3 of K below the third one for some K inside K. So this group is still abstractly isomorphic to K, so it is finitely generating. And you can take product of such groups, and product of such subgroups are called broad subgroups. So basically, you choose some vertices And so you have a bunch of vertices like here, so one on the left, for which you have some diagonal subgroup. You have another one, the one on the right. So you still have a diagonal subgroup. So K itself is like diagonal, but just on one vertex. And you take the product of this, and you will have a finitely generated subgroup of G, which is isomorphic to K squared. And here is another example, which is also isomorphic to K squared because you have only two blocks. So we're able to find like many finitely generated subgroups. And of course, if you take finite index overgroup of this, there's still going to be finitely generated. So if a subgroup is virtually blocked, meaning like if H has a finite index subgroup P, which is blocked, that H is also finitely generated. And now the question is like, can you find other finitely generated subgroups? And sometimes the answer is no. So our main theorem is like for some groups, so first we go to group or torsion GGS group, then every finitely generated subgroup of G is virtually a block subgroup over K. So if you want this to be like a precise statement, you need to precise over which K. So you can do it like, so first we go to group, it's regularly branched over this subgroup. So the normal closure of the commutator of A and B, which is an index 16 subgroup inside G. And you can also explicit what is supposed to be K for GGS groups. So this seems like very specific. So as we go to group or torsion GGS group, actually we have like an abstract version of the theorem. Okay, so before giving you the abstract version, I need just to define the one last notion is like, if I give you a regularly branched group, the definition is that there exists a finite index subgroup K such that so on and so on. So if we called RB the set of all such subgroups on which G is regularly branched, then what we can show that RB has a unique maximal element, which we call the maximal branching subgroup of G. So with that, if you have a subgroup G, which is finitely generated, self-replicating, regularly branched, and you take K to be the maximal branching subgroup, if you suppose moreover that G acts tri-primitively on T, and I will explain that, as trivial branch kernel and as a subgroup induction property, then finitely generated subgroup of G are exactly virtually blocked subgroups. So, okay, in order for this to make sense, I need to define what is a tri-primitive action, what it means to have trivial branch kernel, and what is the subgroup induction property. So tri-primitive action is quite easy to define. So G acts on T. So you need to preserve the tree structure. So it means like the action cannot be primitive even if you restrict it to some level. Like for example, if you look at the binary tree and you look at the partitions 0, 0, 0, 1 on one side and 1, 0, 1, 1 on the other side, since you have to send 0 either on 0 or on 1, then you need to send the blue vertices either on the blue vertices or you send the two blue vertices on the two red vertices. So you need to preserve this partition. So branch group or subgroup of out T will never act primitively on the level. So we say that the action is tri-primitive if the only partitions that are preserved by the action of G are the partitions that are already preserved by the full automorphic group of the tree. So the action is as primitive as possible while still being an action on the tree. Okay, so this was easy to define. Trivial branch kernel, maybe we don't need the exact definition. It's just something that is weaker than the congruent subgroup property. So it just say like the profinite completion is the same as the completion according to some other topology, so the one generated by the rigid stabilizer. So, and now as a last definition, hopefully, so the subgroup induction property. If you have a self-similar group, then a family C of subgroups of G is said to be inductive if it satisfies three properties. So it contains a trivial subgroup and G. Also, this is supposed to be an C, not an X. And also, you want this family to be closed by taking finite index over group. And finally, if H is a finitely generated subgroup, stabilizing first level, so fixing pointwise vertices of the first level, such that all of the section of H are inside C, you want H to still be inside C. So if you look at the definition, then it's easy to show, like, if you take the class of all finitely generated subgroups, then this class is inductive. And we say that a subgroup has the subgroup induction property if any inductive class of subgroups contains all the finitely generated subgroup. So now maybe I can skip some of the consequences. Not sure I will have time for that. So we want to apply like the abstract theorem, so we need to find groups that satisfy all of the conditions. So in particular, we need this group to have the subgroup induction property, and only a few examples are known. So first, the first Grigorchuk groups, this was shown by Grigorchuk and Wilson in 2003. Then the Gupta-Sidki 3 group by Garrido, 2016, and then we generalized the above with Franke, and we show that every torsion GGS group has the subgroup induction property. So now some consequences of our results is like if you have a group satisfying our main theorem, like the first Grigorchuk group or torsion Grigorchuk groups, then you can show that this group is loved. And actually, every group with a subgroup induction property is already loved, but this gives you like an alternative proof of it. You can use it to classify weakly maximal subgroups of G. And you can also use it to classify finitely generated self-commensurating subgroups of G. So I'm mentioning that because you can use self-commensurating subgroups of G to construct irreducible representation of G. And actually, it's one of the only way, for many groups, it's one of the only way to construct irreducible representation of G. So it's why you might be interested in that. And a few words about the future. So some project is, we would like to use this theorem to show like the Grigorchuk groups and the Ribs-Zaleski property. So this might be doable because we have a good description of finitely generated subgroups. We also like want to use it to have some sort of descriptive version of the Olsen property. Like we would like to have an algorithm. If I give you two finitely generated subgroups, then you can decide whether or not the intersection is still finitely generated. So for example, like in the free group, if I give you two finitely generated subgroups, then the intersection is still finitely generated. In general, for general groups and two subgroups, the intersection might not be generated, but you might opt for an algorithm telling you if it's the case or not. And yeah, I don't think I will have most time about the proof. Is like you can just split the proof into three parts. So you say like a subgroup is fully supported if by going deeply enough in the tree, you can find a transversal such that every section is either finite or the full group of G. And then you have this kind of relation between being finitely generated, fully supported, or virtually blocked. So for the Grigorchuk group, all of these notions agree, but sometimes one is stronger than the other one. And blah, blah, blah. I think it's most of what I wanted to say. Let me just check. Oh, yeah. So one important element in the proof was a careful study of almost normal subgroups. So subgroups that are normal inside the finite index subgroup of G, and you can use this to say something about finitely generated subgroup, but I don't think I will have time for details, so I'm just going to stop here. Yeah, I think, yeah, that's it.